Decimal Oscillation, Central Course Program, Amateur Integration of Mission.
Can you send this on to me?
Okay.
I just want to refer to this. But you spent 7 months, you mean?
Actually, more than that.
Actually,
More than that. So those 1 year, your semester is long.
Actually, semester was 6 month duration, but due to political instability, our exam could not. Our exam was not in the time. Actually,
Okay.
first semester we have written our exam in 10 months.
Oh.
First
Okay.
semester and second semester in
We have finished 4 semesters in almost
That's
4
almost
years.
like 2 semesters in our case, right?
yeah, in our case.
So
yeah.
that is why I thought, okay, then we can cover
We
more.
finished, we finished our 4th semester in almost 4 years.
Yeah.
Oh.
In our country, yeah, syllabus is huge and lots of topics was there, and so it takes to teach lots of time, and that's why in the central campus that is small topics, and they cover all the course within a period time frame, and in the affiliated college they could not finish their whole syllabus, and they need to depend on the central college. So our exam dean of office schedule our exam routine, and in that routine there was no exam.
Oh, okay.
Always postponed our exam.
This is your content, right?
So
Yeah.
it's 5.6 and 5.30. Can I run this to you tomorrow morning?
Yes, yes.
But like, I'm
The
done with
first,
this.
yeah, this one you did, right? So, okay, that one is,
Yeah.
okay. Tomorrow,
So you're free at 12?
yeah,
Today is our last class.
Yeah.
today is last class, yeah. So I'm going to give you the final exam.
Okay.
Tomorrow, I'll be in office.
At 12?
Yeah, I think,
And-
yeah.
Okay.
I have a meeting just online, so.
Okay.
Last class December
I'll
5.
head over after my
Yeah,
TA
yeah.
first.
Okay, okay.
Thank you.
So this one, I think
One
you
day
did good job. The only thing here,
Yeah.
when you want to find F1 or F2,
Yeah.
you know that is a functional Q and a capital Q. So if you only do one integral, you have a constant.
Yeah.
That comes to be function of capital Q.
Right.
So you need to find that capital Q from another relation, which is from here.
Okay.
So this I gave you the nice solution or example so you can write.
And I was running around in old.
Yeah, I thought you spend the time and
Yeah.
almost discussion is correct, but I just missed that one.
Okay. Because I
Okay.
got 0. I was like,
Yeah, I
well,
know.
well, let's
You
try this
kind
one.
of missed something, right?
Yeah.
Yeah.
Okay.
No problem. Okay.
Thank you so much.
Alright, today I think I'm going to brief summarize in chapter 10 how to apply the Hamilton-Jacobi equation. Then we do one example. So I may finish a little earlier so you can have time to prepare your final exam for this mathematical physics. now just brief summary before we go to examples. So the chapter 10, our idea or try to introduce the Hamilton-Jacobi theory. This theory's idea is very clear. We start from old phase, right? Old phase space, that is the system we are interesting. With the general coordinates and general conjugate momentum, we call this conjugate canonical variables. Then Hamiltonian this one. Then to solve this difficult, if we use Hamilton equation of motion, then what we do is, okay, let's do the canonical transformation from old phase space to the new phase space, such that in the new phase space, all the canonical variables are constant. So if a constant is all the new Hamiltonian is constant or zero. So by this way, then we go back to see the condition for the canonical transformation such that we can get zero is this equation, right? That is Hamilton-Jacobi equation. So this one, this is since we k equal to 0, then k equal to h plus partial s partial t. So now reduce to solve this equation motion from the Hamilton equation motion to the Hamilton-Jacobi equation. So this one, in principle, we can get the solution S. S is we call the Hamilton principal function. Actually, is the generating function Fi, depending on which type we are going to select. So here, that is actually we are going to do, for example, select F2. Then once we have S, then we can find the solution. That is our goal, right? The equation of motion of system, or the motion of system. Then we also can obtain this new canonical variable alpha beta by the initial condition. All right, so now special case, if the Hamiltonian does not depend on time explicitly. So we have already proved the partial s partial t is a constant. We introduce this one. Then here, so we have the conclusion is s is minus alpha t. Okay, let me use alpha 1. Plus, we introduce the characterized function w. So from here, then this the Hamilton-Jacobi equation is reduced to h just equal to alpha 1, right? And then, okay, just is reduced to Hamiltonian equal to alpha 1. And from here, the solution is w. Then once we have w, so we go to s. Then we are going to, from here, from this s, we go to this. That is the summary, not the step. I just also give a general steps. Step 1. Okay. We first, as we see here, we first need to set which type of the generating function or Hamilton principle that we need. So step 1 is define S equal to Fi. For example, let's select F2. If F2, that means S as a function of Qj, P, capital Pj, right, T. And that is since we already convert or transfer, canonical transfer to the constant, right? So that is a Qj alpha j P. So here, that is the first step. Which one you are going to select? So once you select step 2, find this, in this case, is this one, old canonical variable. In this case, P, right? We have, as we have Q, so P. If you select F1, F3, then this is P, right? Then you need a Q. So that depends on which type you're going to select. The other old canonical variable, here, one of them, because the generating function is half of the old and half new. Once you select one type, you are going to see another one, which is relation partial S, partial Qj, right? Okay. Or depend. Or in this case, right? If in the first case the Hamiltonian depend on time explicitly, if not, we found out this partial S, partial Qj equal to partial W, partial Qj, right? Since here, it is, this does not depend on Q, right? Only W. So that is the second step. Then we have this, okay. Then we go to step 3. We are going to substitute this into this Hamilton-Jacobi equation, this one. So the Hamilton, this one, you can set this one. Set these times Q. 3, 2. Hamilton-Jacobi equation. So Hamilton-Jacobi equation depend, right? There are two types. One is either Hamiltonian Qj, and now Pj is partial S, partial Qj since here, right? 3. Sorry, this is 1. And time plus, okay, partial S, Qj, alpha j, t, partial t equal to 0. That is this case. But if the second case, if Hamiltonian does not, so now 4, depend on 4, this Hamilton-Jacobi equation is Qj partial W partial Qj. Now we have no t, right? That equal to alpha, so I use alpha 1, right? Is this one. So it really depends. Depend on the system. We are going to analyze whether it's satisfied. If satisfied, you just use this one. Okay, so when you substitute this is number step 3, right? Then step 4, we are going to solve. Solve Hamilton-Jacobi equation. And by solve that, we are going to obtain the solution for S. So for S, okay, which is a function of Qj alpha j_t, or S is minus alpha 1t plus W Qj alpha j. Depend, right? Also depend on if a second case, S is this formula. So once we have this, that is step 4. Then in this case, we found from solve this equation, actually usually we should obtain the partial derivative, or partial derivative this one. You don't need to do the integral in this step. Do not need to do. Since the function you will see that's the integral. Just keep that one. Then we go to step 5. Step 5. Okay. We're going to from S to obtain Pj. That is Pj is partial S, partial Qj, right? Or partial W, partial Qj, which is a function, since S and W are function of Qj alpha, so that is Pj still Qj. Here we do not know the solution, but it is function of alpha j. Maybe time may not, if this one does not depend on time, right? So then just keep a general. So that means in general you will have, if I say that equation here, this is number 2, right? So for this equation number 2 here, we have this, and then this is 3. So that is your step 5. Step 5. Then now step 6, we are going to from still from S to obtain Qj. Okay, how to do that? We use this one. Capital Qj is partial S, partial alpha j, right? And this also depends. If it's if j equal to 1, okay, I just keep here. Alpha j. Or equal to just this one, or equal to beta j, sorry, I just use general. Because it's a constant, right? And so because this S is a function of Qj, alpha j, and t, so the beta j is a function of alpha j, Q, sorry. Qj, alpha j, t. This is a constant, but this all the function we call the constant. So that is equation 4. So if you merge the equation 4, then you got Qj is a function of, you see here, alpha j, beta j, t. That is equation 5. So here, I didn't do the details here. If the alpha, if S is this one, so when you do the alpha j is alpha 1, you only have this t. The others have this one. So that details I didn't write down here because either this one or this one, right? So now that is step 6. We obtain this one. Now in this case, you can see we reach our goal. Half of this canonical variable general coordinates a function time, and those are parameters, right? So then from this one, step 7. Step 7. Okay, those is substitute equation 5 to equation 3, right? Now we are going to obtain this one. And this from here, we do not know, but now we obtain here. So you have a Pj is Pj. Now Qj is this one. It's alpha j, beta j, t, and alpha j and t. So now this is equation 6. So now you see these two formula or solution we obtain. And last one, or last two steps is to determine this alpha j and beta j. We do not know, right? So step 8, determine alpha j and beta j. How to determine? We just use this Qj. Qj is alpha j, beta j, t, when t equal to t naught. That is Qj naught, right? I set this and Pj alpha j, beta j, t, set of t equal to 0, that is Pj naught. So from here you can obtain the alpha j as a function of Pj naught, and beta j same. Then finally, you substitute alpha j, beta j into the equations 5 and 6, right? Step 9. Alpha j, beta j in equations 5 and 6. So finally, Qj is function of Qj. Now alpha j is a function of Qj naught, Pj naught, and beta j is also a function of Qj naught, Pj naught, and top. And the Pj is alpha j, so now Pj naught, Pj naught. J, Pj naught, Pj naught, and top. That is fine. Okay, so now let's do one example, see how can we apply the Hamilton-Jacobi equation to solve this system and obtain this dynamics of equation of motion for the system. one dimension, right? Okay, so first, before doing this, we first system in old phase, right? Phase space. We have the Hamiltonian. Here we already write down Hamiltonian. If initially, in general, you have to set up the general coordinates, select the general coordinates, and then you're going to write down the Lagrangian. Then you convert Lagrange to the Hamiltonian. But if you're familiar with this, you can immediately write down the Hamiltonian. Since we already play a lot. Okay, so this one is in old phase, the old Hamiltonian. We know that equal to E. You already proved because T equal to T now, and V equal to V Q, right? We already proved. So satisfy the condition here. Okay, so that is the Hamiltonian. Now we are going to first step one. We are going to select S is F2 type. So F2 type, you can, as I said, you can select any others. It's a function of Q, P, T here. I didn't use index here because only one dimension, J equal to 1, right? So that is the first step, okay? Then second step, P, since here, right? P is partial S, partial Q. Okay, so that we obtain. Then the step 3 is substitute this one into the Hamilton-Jacobi equation. So let's look this case. Okay, so now here Hamilton-Jacobi equation is here. Q, P, T partial S, Q. Okay, let me use R here. That is this one, right? And if we substitute, that means HQ partial S partial Q T plus partial S Q alpha T partial T equal to 0. So that means we are going to solve this one. But now, let's check. Here, this is a, so this is a partial H partial T equal to 0 case, right? So here, since in this case we know the Hamiltonian does not depend on time explicitly, so we have read S is minus alpha T plus W. Then P is partial S partial Q is equal to, this does not depend on Q, so that is partial W partial Q. Then here is this part. So here, the Hamilton-Jacobi equation, if this, let's reduce to this one, right? So that is H Q partial W partial Q equal to alpha. And we are going to, this is equation, this one. Okay, so that is our next job, and we have this one already. Step 3 we finished, right? Now we go to step 4. Step 4, we are going to solve, right? That is how to solve the Hamilton-Jacobi equation. Is this one, right? So now this is this part. All right, so now let's substitute here. Hamiltonian is this one, right? So that is this one, right? So now let's see. Half 1 over half, so half M, and then inside P. P is this one, right? So that is partial W partial Q squared, and plus M omega M squared omega squared Q squared equal to alpha, right? Just substitute. Okay, so now we are going to solve this one from this equation. And from this equation, the key is this one, right? So I move this to the right hand side. Then you will see here partial W partial Q squared is equal to, I multiply 2m, so 2m alpha minus here, mm, so we have from, okay, that's it already, so this one is minus m squared omega squared Q squared. That is, we are going to find this one, right? So if you square this, so the partial W partial Q is square root 2m alpha minus m squared omega squared Q squared. That is, we obtain this. You say, you may ask, okay, I did not obtain W, I did this partial derivative. Yes, let's keep this one. That's why I say do not do this integral, so that means here the W is to the part the integral, right? 2m alpha minus m squared omega squared Q squared dq. If you want to plot some constant, but this constant, since this is only alpha is here, right? So there's only constant, and really constant, you don't plot the matter. All right, so if that's the case, I'm going to, okay, fine. This is W, so S. Because next step we'll go from S to find those, right? So now W is S is minus alpha T plus W, right? So that is, I just dropped this one since you see we only need the partial derivative, so this is not important. So here minus alpha T plus the integral 2m alpha minus m squared omega squared Q squared dq. All right, so that is before step 5. The step 4 we obtain this solution. Even though we do not do these details, later when we come to here, we're going to solve. Okay, so now we go to step 5. Step 5, let's first look this conjugate momentum, right? So P is here, right? Since in this case, the Hamiltonian does not depend on time explicitly, it is nothing but this partial characterized function. Okay. Is this one, right? But we do not know this one so far. Right, so we are going to keep here, as a hint, you see here, it's still function Q and alpha, so still function alpha and Q here. But we keep it, now we are going to find the Q, then we come back to here, right? So that is step 5. Now we go to step 6. Step 6, we are going to find the Q. All right. So this is a function, keep it in mind, not a function Q and R. But no time, since W does not depend on time, right? Now we go to step 6 and the remaining steps. Step 6, right? Step 6, we are going to go is this one, but we need to from here. Because capital Q is partial S partial alpha, right? Now here, alpha is here, right? So S here, S a function alpha here. So there's a 1 and a here. So we have alpha and the 2 terms. Now what you're going to do is first partial S partial alpha here minus T. Minus T. Second one, the inside integral, right? So now we do that plus. And then partial this is square root, so now it's 2m alpha minus m squared omega squared Q squared. And then this you have a half, right? 2m dq, right? do this division inside, right? So when you do this, table, you have half of it and go to down, and then this factor is 2m. Okay. So we have like that, minus t. 2 to cancel, right? So that is m. Now I'm going to take this outside. So I have a 2m alpha because this constant does not depend on q, right? So I take it outside and square root 2m, and then we have another m. So that is m, right? And inside in q, which is 1 minus. Okay, here I have m, so that is m omega square 2 alpha q square. Yes. Then you define. Now we need to do the integral since we need to find the final. So now we are going to do this. Is if we suppose x equal to m omega square 2 alpha q. Square root. Square root m 2 alpha and omega q. So the dx is alpha omega dq. Then we substitute into here. So let's look this integral here. This one is going to be the front, right? Because this appears to be constant in this. So I do this, and that is the left hand side is some function, but right hand side function constant. So we have beta prime. And then I move this minus t to the other side. So beta prime plus t equal to this integral, right? Equal to this integral is m over 2 alpha. Then here you have this, just, I think I can quickly write down. You know substitute in this one, so then finally you can find it is 1 over omega dx 1 minus x squared. You see here, this one go to here, and just divide with omega, then this is dx, right? This is x. That makes sense? Okay, so that is the only one term is this one here. So this integral, we're familiar, this outside, right? Okay. Omega. Arc sine. The variable is x, right? Let me use x first. And then we substitute x. So now I go substitute x again, so 1 over omega arc sine. X is square root m over 2 alpha omega q. Okay. Now you see here, but the left hand side is function time and plus constant. The right hand side is q, so we are going to find q, right? Okay, I use the goal is find q. So now we are going to the right one, so before that we can, let's see, this multiply, define beta is omega beta prime. Then here the left hand side is beta plus omega t, right? Equal to multiply equal to arc sine and 2 alpha omega q. So q is, then you have this. Q, you see, this multiplied, so that is 2 alpha over m, and there's only there's omega here, right? So omega square sine beta plus omega t. That is our solution. See, I didn't do any partial, of course, that partial differential equation is this one. But this one, since it's the first order, is here. We just do the integral. Okay, now the remaining part, we are going to substitute this one into p, right? P here, right? We need this q. sub this Q to here, so you got P. So we just remove those. Okay, now we are going to for P. Numbers K, Q, Q to P. So P is square root 2m alpha minus m square omega square Q square, right? So now let's set here 2m alpha minus m square omega square. Q is here. Q square, so then we have 2 alpha over m omega square, take square root, and then here sine square beta plus omega t. Okay, so you see here, this term cancel, this one cancel. You have same 2m alpha, right? So take square root 2m alpha outside. That inside is again square root 1 minus sine square beta plus omega t, which is cosine beta plus omega t. See, now I have the function p is alpha beta t. Here q is also function of alpha beta t. That is our solution, right? So now when we do this, finally we need to determine what is alpha beta. That is the last step, right? So we're going to that is that. I think I already write down several steps. Step 6 is step 7. Step 8. We're going to determine alpha beta. How to determine? So now let's look this at the t equal to 0 case. So q t equal to t naught is t0. T0. Okay. That is here. So that is 2m alpha over, 2 alpha. 2 alpha over m omega square sine beta, right? And t equal to 0. And p equal to 0. If I say this is q naught, then p equal to 0 is this one, right? So now this one also 2m alpha cosine. So if I use q naught over p naught, then you can see this becomes tangent, right? So here, then this one, this alpha is alpha cancel, right? And then we still have go out, so this is square. 2 to cancel, right? So that is coefficient is here. 1 over m square omega square. This is the denominator, right? And then tangent. Good. So from here, we have obtained the beta. Tangent beta is m omega q naught over p naught. And we obtained the beta. Then how about the alpha? Okay. Alpha, remember, here, right? This is alpha times 20. H equal to alpha. And this is equal to, we already at the beginning, we know that is energy, right? So that is the initial, since it's a constant, initial momentum and initial position. That is alpha. So you see the alpha's energy and the beta is the angle. So what do you mean? we're going to convert or make the kinetical transformation from old phase space to the new, and the new phase is nothing but the kinetic variable. One is energy, another is angle. When we select that, we know the Hamiltonian, new Hamiltonian is 0. Then they are cyclic, so we can solve those, use this Hamilton-Jacobi equation. Okay, so now if we select this Q naught equal to 0, usually just at beginning as equilibrium, right? But this distance, so if you select 0, then you see tangent beta is 0, so beta is 0 right from there. And this alpha still alpha equal to energy, that is equal to the momentum, initial momentum. Now the step 9. Now we are going to substitute beta alpha into the final equation of motion for this dynamics of the system. Is this two, right? This one and this one. So now finally, final solution. Q is equal to alpha is energy, right? So I replace by energy Q. This one. Over n omega square sine beta omega t. Beta is 0, right? So in this case, so just sine omega t. And p, so that is a function of time, right? That is our goal. T. P. P is this one. It's cosine, right? So that is alpha is also energy square root 2 m e. Cosine beta is 0 omega t. And we know this relation between this. It looks like I still have a time. How about I stop at 5, so you have 15 minutes, or you want me to stop here? You prefer?
How much more do you have left?
You what?
How much more do you have left?
Another topic is like a separation, and just and I think I will not discuss the examples maybe on next Tuesday, but give some idea. That's 10 minutes. Okay. If this Hamiltonian is separable, so this is a one dimension, that's fine. But how about this multi-case? If it's separable, you will see the solution become easier since we have many variables, we have several independent. So how to do this? So if the Hamiltonian can be separated into the two parts. One is the first one is only a function of Q1, P1, T, and plus the remaining part. Qj, j not equal to 1, Qj, j not equal to 1. So in this case, then similarly this Hamilton principal function S is also separable. S can also write down S1, Q1, alpha 1. And maybe alpha 10, but only the variable is Q1 is m plus S prime, Q j not equal to 1, alpha 1, alpha n. So in this case, now we go to the Hamilton-Jacobi equation. The Hamiltonian plus partial S, partial T to 0, right? So now we have H1 which is only the function Q1, so that is a Q1 partial S. Now here only partial, because only S1 is related to Q1. Here, so that is partial Q1. And then T plus H prime. The remaining part, Qj, J not equal to 1. And partial S, partial Qj, again J not equal to 1. T plus partial S1, partial Q1, and partial S. Because S1, implied S1 is only Q1, not partial S prime, partial, sorry, with the T. Equal to 0. So if you move this both sides with different variables, so you have this one. Okay, that is equal to 0. So if the left-hand side is greater than equal to 0, then this only function Q1, this only function Q1. So that means this one independent of this. Therefore, if it equals 0, that means this part be 0, and then the remaining part 0. Right? So we immediately got this the H1, Q1 partial S1 partial Q1. T plus partial S1 partial T equal to 0. And the remaining part is prime Qj T not equal to 1. Partial S1 partial Qj J not equal to 1. T plus partial S prime partial T equal to 0. So for this one, it becomes simple. This is like one dimension. Since the variable only one, like Q1 and alpha 1. The remaining. This is for case only one separate. If all separate, then you will see this became one. So that is if, it says, if all OQ is separate, but in H is separable. So the H is correct in terms of summation here and H here, each Hj only function of Qj, Qj, T. Then the S also can write out in terms of summation Sj, Qj, alpha j. Here, this one is alpha can include others. Then this Hamilton-Jacobi equation is reduced to, okay, that's reduced to J, Qj, partial Sj, partial Qj, T plus partial Sj, partial T equal to 0 from an equation. So we can solve this equation individually, and each one is only one variable, same as we just did for this one-dimensional system. Then, after that, for each one you have the solution. So usually the solution you will have Qj as Qj T. It is possible. It is either doable if it is separated. Okay, let me just stop here. Then the next Tuesday, we say 10, right? 10 a.m. and here. And if you have, probably will, if you have no more question, I can take one example for this case. If not, you have question, you can discuss. All right. My hand is dirty. Can you pick up this final design? And pick one of them. I do not know why this.
Can I get one of you just for a second? I have a meeting to attend, so I'm just looking at I think I'm going to sit up with them to distribute the papers, and I'll be back at 6.
That's fine. We'll be here till 9.
Okay, so everyone pick up.
Sure. What? Sit
Huh.
right. Join.
She'll be back at 6. Someone,
6.
someone else is gonna proctor us until
So we
6.
had extra time.
Oh.
So you have more time, right?
Yeah.
That's fine, I will stop here. Okay, so now let's just quickly explain a little bit about these 3 problems. The first one is related to chapter 3, right? So just we introduce the generalized force. Remember that is then try to find relation because definition for general force and potential. Find potential. Then you have once you have potential, you can set up Lagrange equation of motion. Then they obtain this equation of motion and the conjugate momentum. Then discuss whether it is conserved or not. 13 points. Second one, the program, the figure looks like this is a pendulum with a length L is fixed, and also this suspension is also motion on the circle A also fixed. So try to find this Hamiltonian. Of course, you first need to find this general coordinates you're going to select, and then find this Lagrangian, and then convert to the Hamiltonian. How to convert that we learned in chapter 8, right? So yes. So this is actually the problem in chapter 8, related to chapter 8. Then once you have this Hamiltonian, you can solve the Hamiltonian equations. Hamilton's equation, Q dot, QG dot, PG dot, right? Then you describe physically the nature of the kinetical momentum, whether it is conserved or not. And does the Hamiltonian equal to the energy or not, right? So you try the condition. And energy is conserved or not. Number 3 is chapter 9. It's about this canonical transformation. So we have a Jenny function G, which is Hamiltonian of this, actually Hamiltonian, yes, kind of this oscillator, right? 2-dimensional something. So then, as a generating function, obtain the x and y. If you say, I give the equation, right? U, the equation motion. U as a function, the parameter alpha, and alpha in this case, what is the alpha? Remember, if a generator is Hamiltonian, alpha is what? Remember, if a generator is moment, linear momentum or displacement, and alpha is. So just remember this. And I also give you a hint for this. The Taylor expansion over this to the cosine side. I think that is, they only carefully do this because the commutator, I mean not commutator, Poisson bracket here, quantum mechanics here. So it takes carefully to treat that one. All right, and this turn on December next Thursday, right? We have in class. So in class is 3 p.m., right?
3 p.m.
Yes, okay.
So
Of course, we will see you on Tuesday, so we still have a December 6th, we can meet each other.
So the in-class portion will have the same kind of
Yes,
distribution of
also
questions?
three questions, and of course, one of these from chapter 10.
One from chapter 10 will be on?
Yes, we will.
So 3
But
questions?
not so difficult, so just definitely you need to practice or look this notes. That's if on Monday, sorry, Tuesday, if you have
Okay. So like another one from like chapter 8 and chapter 9 will...
chapter, yeah, 3 or 8 or 9 and
Okay.
10. Yeah, definitely there's a one from 10.
Okay,
Yeah.
okay.
Okay,
Thank you.
okay. Yes. Okay, now you switch on your mind to the mathematical physics
Yeah.
now.
We finish mathematical, and then we start classical.
Yeah.
Yeah, and then...
We have just 3 days until Monday, we can read.
Can I see your homework? I just, for the
Can-
first one,
We have
here,
1 hour
you also
time
miss the
again.
one because you know
It's
this
very hard
and
on
the function, a Jenny function is half of the old one, half the new one, right? So you here, I think you miss the Q, the relation Q, because you do the integral only for the
Analytic.
for the
Yeah,
one.
yeah.
Here I give you an
And
example.
that's where we use the Cauchy
If
recipe.
select F1 type, it's Q and the
Cauchy's
theta,
theorem.
right?
You know, it's just,
So then the
it's equal to
F1
zero.
to the partial, if you found this P,
Yeah.
so that is function of Q.
You guys remember the proofs now for Cauchy-Riemann
Okay.
condition.
Yeah, this one,
Cauchy-Riemann
right?
condition, yeah.
From
Yeah,
here,
yeah,
because it's a
okay.
P, right?
And then we plug
P
it
is
into
this one.
Green's
So you do
theorem
the
to
integral
find-
with back to
Can-
Q,
Can you prove?
then you do the P over capital Q.
The residue formula?
Either this one or this one, but then you do this
Then
one, you
you
have
come
a
up from
constant
derivative
be
method.
another function. So this part
take-
term you miss,
Residue
as I just
formula
gave
from-
you.
Is it okay if I
Lorentz
take like
series.
photograph?
Lorentz series
This
is
give you-
converted
Okay, thank you very much.
into
That's
it.
fat axis, in point of the real axis. How can we do that?
You have it?
B n plus b equal to
Yeah,
n,
written down.
g and g naught
It's a closed textbook exam.
Yes, yes.
plus control.
So you need to remember all the formula.
Yeah.
All the formula. which
Remember,
step?
derive,
Close
notes.
check.
Wow.
Close book exam
Yes.
is difficult.
Okay,
It
It's a
builds,
completely closed book exam.
I know,
it builds character.
yeah.
I think I'd do better on closed book exams
Yes,
because I'm forced to.
force you to remember. Yes.
Yeah.
That is training.
Mhm, yes. Chandra, you have the proof for residue?
Yeah.
Residue theorem.
Yeah. Yeah,
And that
written
is
down.
a residue formula for
Yeah.
1 over n minus 1 factorial.
Oh, well, yeah, I know that one.
Another that one.
Yeah.
Lorentz, from Lorentz series,
Yeah.
Lorentz series. Okay, I will put it. Just
Thank you.
Good luck.
Thank you.
Yeah.
I'll see you at noon
See you
tomorrow.
next Tuesday. Oh, you'll see me,
Yes,
yes.
yes, yeah.
is this?
What's this?
Were you guys able to solve the the integrals in the last homework, the 4 integrals?
I solved the last one.
I solved one, that 5 by 4 thing, 5 plus 4 cosine thing.
Mhm. Oh.
Others were difficult, like. Oops. Okay, we have some time.
You're talking about that formula, Jacob?
Yes, yes.
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 DG.
Is this correct?
DG.
DG. Okay, we have b n equal to
1 over 2 pi I.
1 over
The same thing over.
pi I
Same thing over z minus z
Okay.
naught minus
G.
10 plus 1.
g upon g minus g naught
Minus n plus 1. Minus n plus 1.
minus n plus 1. I think not.
Are you writing the first coefficient or the second one? First one is n plus 1, second one is minus n plus 1. Check it out.
Okay. And
I don't understand what are you trying to do. You want to prove that formula?
Yeah.
no.
No, you just need to remember those stuff. That's
Yeah.
Yeah.
Oh,
But I
well,
think
she might ask us to prove it. I don't know.
See, this
He
one,
is
right?
asking to prove that.
No, no,
I
no.
was asking to do this.
You want to, like, I found a better way to prove this. I'll show you guys. Your calculator.
They are completely
These are
out of control.
Yeah.
Nobody's ready for this.
Yeah.
Bn is
I can
z
prove
minus
that.
z naught minus n plus 1.
Okay.
For that, I need
How a n plus
that. I
E.
need
No, a n equal to b n plus
Oh.
p. So
The full of word.
a n equal to
where are you guys A and N B and doing?
z naught p.
Huh? What are A and N B and?
How? These are the constant.
Lorentz series coefficients.
Lorentz series coefficient?
Yeah.
Yeah.
Z minus z naught p.
A n
What are you
equals
trying to do? Actually, what you're trying
Yeah.
to do?
The
I'm
important
trying
thing
to-
is you just have to
uh,
find B1. That's it. B1
B1?
B1 will be the residue.
B1 or A minus 1? B
No.
minus 1?
B1 is the residue.
B1 is residue?
Yeah. Oh, your A and B are different or like what is A minus 1?
Residue?
Okay, the way you okay, like the way I'm doing is completely.
Actually, he is asking me to prove that formula. You guys are out of context.
Okay.
That one formula. Yeah, Jacob?
Yeah, yeah.
Alright.
Yeah. Hold on. I have it here somewhere. In this mess. I better not.
You want to prove for that?
None of this is helpful. Open note, please.
Open note.
Very.
Open note practice.
You guys check the Jordan's lemma proof.
Yeah. You want to see it?
I'm working on it. That's it.
Well,
Okay.
here you
Oh,
go.
Ishiranga. Oh,
Thank you
Ishiranga.
very much, Chico.
Oh, issue.
Oh,
Oh, Mula issue.
hey.
Hey.
For the moment, okay. When I see the paper, I will.
I would look at this. I think this is going to be important. Proving the Cauchy-Riemann condition. I think this will be on there.
Okay.
I'm like sure. I don't think she's
You
evil.
feel?
Yeah.
Okay.
Yeah. I have a strong feeling. So,
I'll take that.
so we start with that
Okay.
to get those conditions.
I just remembered the conditions. That's it. But like
Yeah. But like to derive Cauchy's theorem,
Okay.
we take
Would she ask this one?
maybe, but we just write Green's theorem and plug in those values for that condition, and then
Okay.
this comes 0, this comes 0.
Okay. To get
And
the
then-
code.
Yeah, and then
Oh.
that's Cauchy's theorem where the contour integral of f of z dz equals 0.
Oh.
So,
That will be. Okay, I have this part, but like I didn't think that it would be there, so I have to check this out also. Ah.
you know the saying. If it's not on there, it's gonna be on there.
Okay. Now I saw this guy, like another guy, prove the same Jordan's lemma using a different technique. That would be fine, right?
Maybe, but like the only condition is that when m is greater than 0, so in this case m is equal to 1, and if f of z tends to 0 as z tends to infinity, so like when z tends to infinity, then that will go to 0.
Yeah.
So like then we can say that this goes to 0 because of Jordan's lemma.
Yeah.
These are the two conditions that have to be met. So if m is greater than 0, and if that goes to 0 as z goes to infinity. So yeah, it says it all right there in the first, and that's just what she did in class.
Oh, very much.
No.
Oh,
On my camera's battery.
I was about to die.
I'm about to die too. I'm about to pull up the lecture.
No, if this was an open book test, we could easily like score
Yeah.
100.
Yeah, but that's a challenge in this class.
Yeah, I mean, no, it's mathematics. Like, I mean,
I know.
plus now it is not. I mean, we are not school kids. Like, let's say we are doing research, we usually go through internet and like refer stuff.
Yeah,
So what's the point?
I know.
that's the point.
Yeah.
That's not the point. We need to make it.
I stopped
Oh
by.
yeah. You're finally eating it. Yeah.
I stopped by hearting stuff like back in 2019, and now I'm so bad at remembering stuff.
We're not supposed to be remembering things. We're not built to remember things.
Yeah, and then.
Oh, it's a tasty though.
Oh, that is the residue theorem, right?
What's the integral formula?
I'm pulling it up. I'm.
I have to remember this also. When I see stuff. What is
I have
that?
done this.
Very nice.
How
Now
did
I
you
go through this.
So you take minus definitely.
First derivative of f of g naught equals to limit
C equals R, okay. So you take Z as Z plus this thing. So this becomes okay. Then you get. Why did you limit rho to 0?
Huh?
Oh,
Oh,
okay,
yes,
okay,
oh,
got
yes,
it,
the
got it,
definition.
got it, got it. I think that's it, sir. Okay, I have to. That's it. Somehow I have to do. Thank you very much.
Basically, write this down. I'm betting my life that this is on there.
This will be there.
Like, as soon as we get it, if I see it, I'm gonna smile. I'm gonna be like,
I have to write like I can't. I had to write about thrice
hold on.
to remember.
There's a mark.
First I'll write looking at it, then I'll write.
Right, go,
Yeah.
go. Time, we're losing it.
And that also. Oh.
Oh, on the back, this is a B. Whoops. I wrote U, that's B.
Okay.
Yeah.
Oh, just the
Yeah.
limit, right? Yeah.
Yeah.
Oh. Okay, this thing. What's it? The master code, the
You can now you can find the second derivative, third derivative, and you can generalize nth derivative of g naught equals to n factorial divided by 2 pi r.
Alright, just leave it up there, don't erase it.
Shall we leave it there while doing
I-
the exam?
Yeah, just leave it there.
My writing is fine.
Yeah, I'm trying to write it down back again and get things done.
I think this time you will get 100 points.
Really?
Yeah. Your handwriting is superb.
Oh. My god. dx dv dy.
You are writing this?
Yeah.
Wow. Feel like professor.
Professor Chandra.
Dr. Chandra.
Dr. Chandra.
Why is that? Who cares? Just remember it.
The thing is, last time I remembered everything and forgot to raise e to the power. And then screwed the whole question. So, that's the thing with remembering stuff.
Remembering, make it muscle memory. Write it until you don't even remember it. Just your hand remembers it.
Oh.
I don't think I can prepare it anymore. I'm just ready just to have it over. So, tensors. What kind of questions will she put on there? I have no idea. Is this covariant or not? Please be on there.
Just imagine quantum and classical being closed book text.
Yeah.
It's not. Okay, so just to say that you theta. That is equal. Okay, this. Why did you suddenly put the limit to 0 to 2 5? Because it's a circle, right? Okay, great.
From where?
to find that.
Oh, because it's like going
So
around.
for angle
circle.
theta, the
That's-
limit will be 0 to 2 pi.
Right?
Yeah. That's what contours. It's a closed loop.
Right.
So yeah.
So 2 pi I. And then what you did
Simple.
was
Cool.
subjected
Order
explicit
one.
norm, right?
H of z over g of z, residue of
I.
f of z.
You still recording?
I think it died.
You know,
Okay.
Chandra.
Oh, your both battery have died.
Yeah.
Both cell.
Both.
That's good.
We had to prove Jordan's lemma.
I don't want to remember this.
In exam,
I just want
Yeah.
to leave this behind.
so you're gonna ask that question?
She said so, right?
What?
To prove Jordan's lemma?
She said to know it.
No?
She said to know to like kind of know. A
But
little
I
bit
think
of
I
it.
think she will not ask that question.
Yeah.
That type of question I don't like.
She even asked tensors, so.
Oh my god. Please do.
Okay. Which one?
You have the Jordan lemma?
Oh, good. Go and solve.
Oh, that's right here.
He's trying to solve. Let's see.
Not I'm trying to solve, but I'm practicing.
Okay.
What did you like? Here, I think you do it, Chandra? You took the H out?
That's out, and f of g is this formula I inserted that.
There?
Yeah.
For
One is z minus g naught
For
minus
it. to this one, right?
plus x. Yes.
Okay. Okay, good. So, see, how did you, where did this H come from?
Z minus z naught.
Okay,
Z
okay.
minus z
Okay.
naught. You got it?
Just a simplification, right? Yeah.
Okay, good.
Thank you very much.
Oh,
Yeah, I got the point.
okay.
And then comes the job.
The body is very dirty.
You didn't need to erase that. Just leave it up there.
It's dirty boy.
Daddy.
Don't do it. Do it. Do it.
We have new professor today. We have new professor.
Professor Chandra.
Professor Chandra.
He's always he's joking and making fun of others. But you get to make fun of others.
Oh my god, that's a nasty one.
Yeah.
The only thing I was able to solve was 5 plus 4 cos theta thing. Other 4 I could.
5 plus focus theta.
Oh.
Why you guys are not giving the importance for Fourier series, Fourier transform, Laplace transform?
Fourier series, Laplace transform.
They will come, right?
Huh?
They will come, right?
Yeah.
For Laplace, she needs to give the inverse, otherwise we can't.
Yeah.
Yeah. Otherwise we are done.
Oh.
Maybe we could have some stuff on the farm also.
No.
So the recipe of that will be, we have to remember the formulas. Fs,
This is important.
SFS minus F naught, S square Fs minus SF naught.
So pretty much with
Dash,
every
yeah.
derivative, just multiply by an s and minus. You know.
This do we have to remember? Oh, would she keep?
I don't think she will get this. Because you know, you can derive this, but
Yeah, and we have the, we write this.